Hello, so today we're going to dive deeper into what are empirical and molecular formulas. We've touched on this in the last couple of units. However, now we're going to really dive deeper into what they really mean and how to actually determine what the empirical and molecular formulas are. Because, depending on what you're working with, determines what type of stoichiometry you can do, which will be the next unit that we're going to be truly diving into. So just to kind of refresh, empirical formulas, they're the chemical formula that represents the smallest whole number ratio of element subscripts. So the smallest whole number ratio between the elements, the least amount of elements you need to actually have the chemical properties of that particular formula. Now, ionic compound formulas are already in the simplest whole number ratio. They already represent one single unit of the lattice that ionic compounds form. However, covalent compounds is where it really needs to be expressed because empirical formulas can depend on the experimental or literary context. Some covalent molecular formulas are the exact same thing as their empirical formulas, and then there's covalent compounds where they have two different molecular and empirical formulas as well. So let's take a look at some examples. So calcium chloride is an ionic compound, so therefore its empirical formula is already its molecular formula. And so there's a ratio between the calcium atoms and the chlorine atoms. So for every one calcium atom, there are two chlorine atoms. And that's represented by the subscripts here. Take another look at magnesium sulfate, also ionic, so we know that it's already in its empirical formula state. But there are three different types of atoms in it. So between magnesium, sulfur, and oxygen, there's a 1:1 to 4 ratio because of the one that's invisible here, one that's invisible here, and the 4 that's here. Now, we get to CH2O. This is the empirical formula for glucose, which is C6H12O6. With that common multiple of 6 in between it, it's able to reduce those subscripts down to where it's 1 to 2 to 1. So for every carbon, hydrogen, and oxygen that's in glucose, there is a 1 to 2 to 1 ratio between those atoms. So when I times this by 6, I get the C6H12O6. CH, okay, this is going to be ethane, okay, this would be ethyne. Excuse me. So this would be ethyne. So there's a 1:1 ratio because it's C2H2. So with ethyne, its empirical formula is CH instead of the C2H2. But since ethyne typically has C2H2, there's a common multiple of 2, which you can reduce it to 1:1. So for every carbon, you have to have one hydrogen. Okay, and that's where that 1:1 ratio comes from. Now the molecular formula, just as a refresher, is the chemical formula representing one unit of the compound, one unit of the ionic compound or the covalent molecule. Okay, ionic compounds have molecular formulas that are the same exact thing as their empirical formulas. Okay, so there's nothing really worry about ionic compounds. Covalent compounds may or may not have the same molecular formulas as their empirical formulas. It just depends on the compound itself. So we're going to take a look at this. So the chemical name, the empirical formula, and the molecular formula just kind of show the differences and similarities between them. So sodium chloride, okay, is NaCl. Since it's ionic, it's going to have the same empirical and molecular formula either way, okay. Glucose, which we talked about before, the empirical formula on the previous slide was CH2O, okay. The actual molecular formula for glucose is C6H12O6. But again, there's a common multiple of 6. So if I divide all these subscripts down by 6, that's where I get the 1, the 2, and the 1 for here. Okay, so I can reduce these subscripts down to a simpler whole number ratio. Okay, if I was dividing them down and one of these subscripts became a decimal, then that wouldn't work. They have to be whole numbers. Ethene, which is CH2 as an empirical formula. Okay, so ethene is 2 carbons with a double bond in between them. Its actual is C2H4, so common multiple of 2. So these can be divided down to a simpler whole number ratio. So that 2 becomes a 1, and then the 4 becomes a 2 here. And then methane is CH4. Okay, now the thing is that there's not a common multiple between 1 and 4 except for 1. So if I divide 1 by 1, it's still going to be 1. If I divide 4 by 1, it's still going to be 4. So methane's empirical formula is the exact same as the molecular formula. Okay, because if I try to reduce it down by any other number, it will form a decimal, and that's not what we want. So unknown compounds. Through experimentation, chemists are able to identify the amount of particular elements within an unknown compound. With this information, a molar ratio between those elements that are present within the unknown sample can determine the molecular or empirical formula of that sample itself. So with this experimentation, we can actually identify unknown compounds by just knowing how many atoms of what are in the sample, and we can determine empirical formula, and if we weigh that sample, we can determine the molecular formula of it as well. So types of experiments, just for the heck of it, that we can use to determine if you go on further into science, these are the type of experiments that you can do. Nuclear magnetic resonance, as called NMR. I've done a lot of that. Very, very useful technique. X-ray photoelectron spectroscopy, XPS is also another way it says it. I've played around with that a lot. Again, if you want to talk more about this experimentation, please come talk to me. Acid-base neutralization is another way. If you go into higher levels of chemistry, especially just like general chemistry for college level, you'll be doing this a lot as well. Fourier transform infrared spectroscopy, it's a mathematical approximation in regards to how the bonds wiggle and jiggle, and that can help determine what type of bonds or what type of atoms are occurring. And infrared means the type of energy or light that's given off by that. So this is an example of an infrared spectrum for bromomethane. So that's going to be methane with a bromine attached to it. But what we can do is that based off how light interacts with those atoms and how they jiggle around, they present certain spikes in certain numbers. And just based off the spectrum, we can say, oh, it includes this molecule. And these different lines represent, CH bonds and then CBr bonds and so on and so forth. So this is a very common way in which we can determine the composition of certain molecules and compounds. And another one is ultraviolet visible light spectrum spectroscopy, which is called also UV-Vis. I've played around with that a lot as well. So determining empirical molecular formulas, we're going to kind of dive into how these problems work. We'll do it step by step, and I'll give you a couple of examples on how to do this as well. Again, if you don't have a calculator or notebook, please get that out so that way you can work along with me. Feel free to pause this video. There's going to be a couple of slides that have a lot of math on it. I've tried to set it up to where it kind of goes part by part, so if you need to stop it, if I'm going too fast or anything, feel free to do so. Otherwise, if you have other questions after this, please come talk to me and we can kind of break it down further if need be. So to begin, if you're not given a sample size, if you're not given a weight of a sample, it is safe to assume that you have a sample size of 100 grams. I know that's a weird assumption, but just go ahead and make the math a whole lot easier. So assume that the sample size is 100 grams if I don't specifically tell you what the sample size is. This is to mimic the 100% associated with the calculations, okay? So if I have 100 grams, okay, every gram of that is equivalent to 1%. Therefore, 100 grams is 100% of the sample. If you assume the sample size, you can convert the percentages that I give you in the problem for each element or compound or whatever to grams to fit the assumption made, okay? So if I say that the sample is made up of 42% hydrogen, you can assume that out of the 100 grams, there's 42 grams of hydrogen. And again, that's another example. So if I say 17.87% of carbon is of the 100 gram sample, then I can say that there's 17.87 grams of carbon. Okay. With the mass of each element, you determine the moles of each element within the sample. So this is the next step. So, and then what you do is after you determine the moles of each element based off the grams that you assume, okay, you divide each calculated mole amount by the smallest number of moles calculated. And I'll define that here in a little bit in just the example. This can be a little confusing at first, but we'll just demonstrate it further in practice problems both on this video and in class, and you can come talk to me more about it if you need to. And then you round the resulting calculations to the nearest whole number if needed. Then the whole number of moles that are produced from that calculation you will use as subscripts for the empirical formula, or the molecular formula here later on. I'll show you that too. So let's do a practice problem. So what is the empirical formula for an unknown compound that is comprised of 73.2% carbon, 10.7% oxygen, and 16.1% hydrogen? Well, the first thing you ask yourself, do these percentages add up to 100%? If they don't, you need to come ask me, and that way I can adjust it, because if it doesn't, you can't make the assumption of 100 grams. But if it does, then you should be good. So assuming that I have a 100 gram sample, since I don't give you a weight of the sample in the problem, what you can do is you can convert these percentages straight to grams. So I can say 73.2% of carbon is 73.2% of 100 grams, which is 73.2 grams of carbon. Then I do the same thing for oxygen. I do the same thing for hydrogen. So now I have my masses of each of those elements. Then what I do is I'm going to determine the moles of each element using the molar mass given on the periodic table. So I'm going to convert the grams of carbon to moles of carbon. You should get 6.09 moles of carbon. Then I take my 10.7 grams of oxygen and convert it to moles of oxygen, so you get 0.69 moles of oxygen. And then convert my 16.1 grams of hydrogen, and you should get 15.94 moles of hydrogen. Now, the next thing is that you have to say, okay, out of these calculated moles, which one is the smallest? Well, this one is the smallest because it's 0.69 compared to the other whole numbers. So what I'm going to do is I'm going to take 0.69, and I'm going to take 6.09 divided by 0.69, 0.69 divided by 0.69, and then 15.94 divided by 0.69. I'm dividing each one by the smallest number of moles. And what that does is it reduces it down, the formula, to the empirical formula, to the smallest whole number ratio that is required for that to have the chemical and physical properties that that molecular sample has. So what I'm going to do is that I'm going to divide by the lowest number of moles, which is the oxygen. So I'm going to take 6.09 moles of carbon divided by 0.69. I get 8.83, and then I can just round that up to 9 moles of carbon. And then I have 0.69 moles of oxygen. Divide that by 0.69. It's going to be 1 mole of oxygen. Now, one thing to remember is that every empirical formula that you solve for, you are always going to have, before you, if you need to do some extra stuff, which I'll show you here in a little bit, you're always going to have one subscript that is 1, because that is your limiting factor for that formula. Okay. If for some reason there's a decimal issue, this may round up to like 2, but you should at least have one subscript that is 1 or one subscript that is 2 in the empirical formula. And then I do the same thing for hydrogen. I get 23.33. That's pretty close, so I round that down to 23 moles. So my empirical formula, I just plug in what I calculate for the moles as the subscript. So my C becomes 9, oxygen has 1, and then H is 23. So that's my empirical formula for that particular unknown compound. All right, so if you're given the molar mass of the unknown sample in the problem, you perform the exact same steps for an assumed 100-gram sample to determine the empirical formula of the unknown sample. So what you're going to do is, if I give you a molar mass of a sample, you can already say it's like, oh, I'm going to calculate the molecular formula of this thing. But to do that, you have to calculate the empirical formula. So I'll give you percentages. You assume 100 grams, you determine the empirical formula, and then we'll use the actual mass of the sample to determine the molecular formula. So this assumption is still valid for the empirical formula, but you can't use this assumption for the molecular formula. Once you have the empirical formula, you can determine the molar mass of the empirical formula. Okay? In other words, determine the empirical formula weight. So as soon as you get your empirical formula, add up the gram atomic weights or the molar masses of each element based off the subscripts that you come up with, and determine the molar mass of that entire empirical formula. Then you divide the given molar mass in the problem, the molar mass of the sample, by the empirical formula, and that determines what's called a molar multiplier. And you round to the nearest whole number if needed. So if that molar multiplier comes out to be a decimal, round it to the best way you believe possible. And then what you're going to do is you're going to take that molar multiplier and you're going to multiply it by your empirical formula. And what that's going to do is that molar multiplier is going to multiply for every subscript, and then that will turn it into the molecular formula of the unknown compound. So let's do an example. So I have a compound that contains 45.25% nitrogen, 34.64% oxygen, 20.11% calcium, and the molar mass of the compound that I determined was 111.37 grams. Determine the empirical molar mass of the empirical molecular formula of the compound. So I'm still going to assume a 100-gram sample because I need to calculate the empirical formula first. So assuming a 100-gram sample, I convert those percentages straight to grams. Okay, so 45.25 grams of nitrogen, 34.64 grams of oxygen, 20.11 grams of calcium. Okay, then I convert them all to moles based off their molar masses. So I'm going to solve for the moles of each one. Okay. Then I'm going to ask myself, again, what is the smallest number of moles? Well, the smallest number of moles is calcium, so I'm going to divide each of these numbers by 0.5. Okay, so I'm going to divide by the calcium number of moles that I calculated. So I'm going to get around about 6 moles for nitrogen, 4 moles for oxygen, 1 mole for calcium. So my empirical formula based off those moles has become calcium 1, N6 based off the 6 moles here, and the oxygen 4 based off the 4 moles here. Then what I do is I need to calculate the molar mass, the empirical formula weight of this empirical formula that I just calculated. So if you do that, you should get 188.07 grams per mole for that particular empirical formula. And then what I'm going to do is that I was given a molar mass, or the molecular mass of the compound, that the unknown compound that I know of, and it was 111.37. So what I'm going to do is I'm going to take the 188 grams per mole and divide it by my 111.37. Okay, and that's what it's saying, is that how many times does this mass going into this empirical formula? Well, it's about 1.69, so you can just roughly say that's 2. Okay, this is now your molar multiplier. And so what you do is you take this 2 and you're going to multiply it by this empirical formula, and there's subscripts. So it's going to be 2 times the empirical formula, and you're going to get Ca2N12O8. So then your molecular formula is Ca2N12O8. Okay. The way you can check yourself is that there is a common multiplier of 2 between this one and this one. I can't reduce this further down because there's no common multiplier between 1, 6, and 4 besides 1. So if I divide everything by 1, it's going to stay the same. If I do any other number, it's going to turn it into a decimal, and you can't have a decimal in an empirical formula. Okay? So there is a couple exceptions to the rules in regards to rounding and everything like that. So during the calculation of the empirical formula, if you encounter a molar ratio or a molar amount that you calculate after doing the gram atomic weights and converting to moles, and it comes out with a 0.5 decimal place right in the middle, what you have to do is that before you can determine your empirical formula, you have to multiply all those moles by 2. Okay? So what I do is I just had this random example. I calculate 3.39 moles of carbon, 5.03 moles of hydrogen, 3.39 moles of oxygen. Well, the lowest is the same for both carbon and oxygen, so I'm going to use 3.39. Well, what happens is when I divide those by 3.39, I get 1 mole for carbon, 1.5 moles for hydrogen, and 1 mole for oxygen. Well, since 5 is right in the middle, you can't assume that you can round up or down. So what you have to do is you have to times these by 2, and you get 2 moles of carbon, 3 moles of hydrogen, and you get 2 moles of oxygen. So your empirical formula turns out to be C2H3O2. And again, their common multiple between them is only 1. So this is the smallest whole number ratio. The reason why we couldn't use this is because there was a decimal here. Okay? So you can't have a decimal within an empirical formula. It has to be a whole number. So we use the multiple of 2 to convert it to a whole number. All right, so a little bit longer video than usual. It's very, very important that you know this. So again, if you're having any trouble with the calculations, didn't understand something in this video, please come talk to me, talk to a friend, whatever you need to do. You can email me, come by, whatever you need to do. So more than welcome to help you break it step by step. I don't know why that was going on. And just come talk to me if you have any other problems. Thanks for watching this video, and hope to see you next time and in class.